Okay, so we'll start, Nishad. Yeah, just give me.
Okay,
Yeah, so I'll just introduce you.
sure. Thanks.
So, I mean, we have today with us Professor Nishad-Kothari from IIT Madras. He's a professor in the Department of Computer Science and Engineering, and his area of research is graph theory. So, he started out as an engineer from BITS, then he switched to sort of theory, CS, and pure maths. So he did a master's in Georgia Tech and then went on to do a PhD at the University of Waterloo. Then he had postdoctoral positions in Vienna, in Brazil, and then he returned to India and joined IIT Madras. So his research area is matchings in bricks, if I'm not mistaken, or counting matchings in bricks. Yeah.
Well,
So, but
perfect matchings, basically. Yeah.
so he's an expert in perfect matchings, and uh, today he's going to talk about how to count the number of perfect matchings and Pfaffian orientations. So, I mean, let's welcome him with a round of applause because it's something which he's doing for us out of his, goodwill. So, thank you, Nishad. So, please give him a round of applause first. I can hear the applause because the number of participants is less, so the applause sound is less.
That's okay. In
But
a
okay,
course like that, we don't expect too many people.
yeah. So you can start. I'll switch off the video so that you are not distracted. Is it fine
Sure.
or yeah?
I'm okay with it. Yeah. Yeah.
Because it will be just you in the video.
Right. Yeah.
Okay.
Okay. Yeah. Good afternoon, everyone. Thank you for joining. Um, so yeah, I'll be talking, and thanks a lot to Manjul for the invitation and for the introduction. Yeah, so Manjul and we met when I was a postdoc in Vienna and he was doing his PhD there. We had the same host, Ilse Fischer. So yeah, thanks a lot, Manjul. And I will be talking about counting the number of perfect matchings and Pfaffian orientations. We will come to what Pfaffian orientations means eventually. But I assume everybody knows what perfect matchings are. Let's just start with a quick example. And if at any point you have any questions, please interrupt me. Um, so here is an example graph. And let's see what a perfect matching is. It's a set of edges, say the red colored edges. So that if you look at any vertex, at that vertex, there is exactly one red colored edge incident. If I look at this vertex, I have exactly one red colored edge incident at this vertex. And that is true for every vertex. Therefore, that is a perfect matching, right? And perfect matchings and matchings in general. So in matchings, you don't need to match all the vertices. I can also have zero red edges incident at some vertex, and that is a matching. But I won't be concerned with matchings. I will be mostly concerned with perfect matchings. And both matchings and perfect matchings have received a lot of attention in not just in graph theory, but also in combinatorial optimization, enumerative combinatorics, various other fields of combinatorics and theoretical computer science. Um, and a lot of questions have already been answered. For example, you can ask the question from a computer science, theoretical computer science point of view, given a graph G, does it have a perfect matching? And yes, that can be figured out in polynomial time. And there are good algorithms for that problem. However, there are also open problems, or there is also some bad news in some cases. One such example is counting the number of perfect matchings. So you can ask the question, is it possible to count the number of perfect matchings in a graph? Of course, if you allow yourself to have exponential time, clearly that is possible. But of course, we want to compute things efficiently. So I'm going to add in poly time. If you are not too familiar with theoretical CS concepts, you can just say efficiently. And the answer to that is unfortunately no, unless P equals NP. So this was done by Valiant in 1979. The answer to this question is no, unless P equals NP. And it's a very famous conjecture in theoretical computer science that P is not equal to NP. So if this conjecture is true, then definitely there is no way to have a polynomial time algorithm to count the number of perfect matchings. Are there any questions or concerns at this point? Is everybody with me? Okay. If not, I will continue. Yeah. So then the question is, can we still do something? Can we still well, by the way, before we go there, let me also mention that this is not even true for bipartite graphs. Even for bipartite graphs, there is no polynomial time algorithm unless P equals NP. So even if you change the question and you put bipartite, even then the answer is no. And just to remind you, what is a bipartite graph? A graph is bipartite if you can color its vertices with two colors so that all edges go from one color to another color. So this graph here is bipartite, right? Another way to think about it is you have two sets of vertices and all edges should go between these two sets. You can't have any edge like this once you fix the set of vertices, the partition of the vertex set. Okay. So even for bipartite graphs, the answer is no, unless P equals NP. And the reason this is significant is because a lot of problems in matching theory, they become easy for bipartite graphs. However, this is not such a problem. Okay. All right. Okay. So then one can ask the question, okay, fine, we can't solve this problem for all graphs in the world, but are there rich classes of graphs for which we can solve this problem efficiently? Right. Are there rich graph classes for which, sorry, one may compute number of perfect matchings efficiently? Okay. So why do we care? So just to give you some background and motivation, this problem has received counting number of perfect matchings, and in general, perfect matchings have received a lot of attention. And the particular place where this question was investigated, one of the areas is theoretical physics. So in theoretical physics in the 1960s, there was a lot of interest around this problem around counting the number of perfect matchings. Of course, physicists were not really concerned with graphs and perfect matchings. They were trying to count something in molecules, some kind of arrangements. And it turned out whatever they were doing was just a special case of counting the number of perfect matchings in certain graphs. Okay. So in theoretical physics, this is, by the way, called the dimer problem. And this term dimer is coming slightly from a different way of looking at perfect matchings, which is related to tilings. So if you have seen tilings, tilings and perfect matchings, or tilings and matchings in general, are just two different ways of looking at the same concept. Okay. Of course, this is assuming certain things on the tiles. What do the tiles look like? Okay. So this is one place where the problem was investigated. And one of the things the physics folks did in 1960s they found one rich class of graphs, planar graphs. For planar graphs, yes, you can compute the number of perfect matchings efficiently. Okay. And in this talk, in today's guest lecture, I want to tell you why this is true. Why can you count the number of perfect matchings in planar graphs efficiently? Yeah. Does everybody know what planar graphs are? Just to remind you, a graph is planar if I can draw it in the plane on a piece of paper, if you like, without two edges crossing each other. For example, this graph is planar. However, if I make a slight modification, this graph is not planar. This is famously called the triangular prism. And this is a famous graph called K33. It is a complete bipartite graph on 3 vertices of one color and 3 vertices of the other color. Therefore, it's called K33. Okay. Okay, so this is a planar graph. However, one can prove using some topological properties of the plane that this is a non-planar graph. There is no way to draw this graph in the plane on a piece of paper without two edges crossing. You can see here, two edges are crossing each other, right? So it turns out for all planar graphs in the world, you can compute the number of perfect matchings efficiently. Are there any questions or concerns at this point?
No.
Okay. All right. So why is this true? So it turns out they needed a new way of looking at perfect matchings, and they basically needed a different kind of algebraic way of looking at this problem of counting the number of perfect matchings. So I want to tell you about that. All right. So I'm going to tell you about a different viewpoint. However, this viewpoint is not going to work for all graphs. Okay. That is a caveat. It will work for planar graphs, but it will not work in general for all graphs. Okay. So I want to slightly take a detour now and talk about skew symmetric matrices and relate them to oriented graphs. Okay. So you all know what a skew symmetric matrix is. So we will see them. But as an example, let me take let me take an orientation of a graph. So here is my graph. And what do I mean by orientation? So this is my graph G. Maybe I'll make it smaller. Okay. And now what I will do is I will put some directions on the edges. Okay. And that will be called an orientation of G. So I'll just put some directions. Let's see. I'm not going to worry too much about it. I'll just put some directions on each edge. Okay. Let me label the vertices 0, 1, 2. Let me start from 1 maybe. 1, 2, 3, 4, 5, 6. Okay. And the same labels here. 1, 2, 3, 4, 5, 6. Okay. So I have, this is an orientation of G. An orientation of G. Okay. And now what I'm going to do is, I am going to give a sign to each perfect matching of this graph with respect to this orientation. Okay. So when I say perfect matching of a directed graph, I simply mean perfect matching of the underlying undirected graph. Okay. But I'm going to give a sign to each perfect matching with respect to this orientation. I'm going to tell you how the sign is computed. All right. So first, let us check some perfect matchings. Let me take one perfect matching. This is a perfect matching we saw earlier, the red colored perfect matching. And let me take one more perfect matching, the green colored perfect matching. Sorry. Are the colors visible, red and green?
Yes.
Okay, thanks. So I have two perfect matchings here, red and green. I'm going to give them names. Green is M2 and red is M1. Okay. So how do I compute the sign of a perfect matching? Let's see. Computing the sign of a perfect matching with respect to an orientation. Okay. Here is how you do it. And of course, I will explain later why all of this is nice. But right now, I just want to explain to you how to compute the sign of a perfect matching. So, sign of the red perfect matching, sign of the red perfect matching with respect to the orientation D1, D1 is my orientation, is the sign of the following permutation. And I will tell you what the sign of a permutation is. In case you don't remember, that's okay. So I'm going to put all the vertices in the first row. So I'm going to write down a permutation here. 1, 2, 3, 4, 5, 6. And now for every edge that is in my perfect matching, I'm looking at the red perfect matching. For every edge that is in my perfect matching, I will put down, first I will put down the tail, and then I will put down the head. This is called the tail, and this is called the head of an arc in a directed graph. Okay. So let's see. I will take one edge. Let's say I take 2, 5. 2, 5 is going from 5 to 2. So 5 is the tail and 2 is the head. Then the next edge is, let's say I'll take any edge. The order in which I'm picking the edges does not actually matter. You can think about it later. So I will pick the edge 4, 6. 4, 6 is going from 4 to 6. So the tail is 4 and the head is 6. And then I will take another red edge 1, 3, which is going from 3 to 1. So the tail is 3 and the head is 1. This is the permutation I am looking at. What is the sign of a permutation? Can somebody tell me what is the sign of a permutation? If you remember it, I'll give you a hint. It is -1 to the power something.
Okay, they've forgotten.
That's okay. Anybody in the video call? It's -1 to the power something. Okay, no worries. It's the number of inversions. So what do I mean by inversions? Let's just count the number of inversions. Okay, then it will be clear what I mean by inversion. So here is a way to count the number of inversions. Draw a line from 1 to 1, draw a line from 2 to 2, draw a line from 3 to 3, draw a line from 4 to 4, draw a line from 5 to 5, and draw a line from 6 to 6. I mean, of course, I'm using this word line kind of vaguely here. And count the number of intersection points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is basically the number of pairs I comma j, where I appears before j in the first row, however I appears after j in the second row. Okay, so I and j have been inverted in the permutation if you write it in this way. So let's just make sure 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, that's 10. And that is +1, of course. So the sign of the red perfect matching with respect to this orientation is positive. Now let's look at the sign of the green perfect matching. With respect to the same orientation. It is the sign of the following permutation. Put 1, 2, 3, 4, 5, 6 in the first row. And for every edge green colored, I'm going to put the tail followed by the head. So 1 followed by 4, 5 followed by 2, and 6 followed by 3. And now let's compute the number of inversions. One, two, three, four, 5. 5 inversions, is that correct? Okay. So this is what is the sign of a perfect matching. Is that okay?
Yes.
Okay, thank you. Are there any questions or concerns at this point? Is everybody happy with how the sign of a perfect matching is computed?
Hello, sir. Yes, so I had a doubt.
Yes, go ahead.
In the the way in the order in which we write 5, 2, 4, 6, 3, 1 in the first one,
Yeah,
which edge we choose first?
right.
Matching
It
edge.
doesn't matter. So even if you choose, so the perfect matching edges, whatever order you choose them in, you can do some, it's an easy proof that the sign will not change, even if you change the order in which the edges are listed.
Oh, okay. Thank you.
Yeah, but that's a good point. Thanks. Okay, so the order in which you list the edges in the second row, it is not going to affect the sign actually. Okay, basically the number of inversions will change by an even number, and because it changes by an even number, it will remain the same sign. Yeah. Any other questions, concerns?
No.
Okay, good. So now let me tell you what is the Pfaffian of an orientation. The Pfaffian of an orientation is simply the sum of the signs of all the perfect matchings. It is simply the sum of the signs of, take all the perfect matchings of the graph. This is my set of all perfect matchings. All perfect matchings of the underlying undirected graph. Okay, so perfect matchings of this graph. And for every perfect matching, you just take the sign and you just sum up the signs of the perfect matchings. Okay, this is what is called the Pfaffian of an orientation. All right, so for this particular orientation, the problem is I have only counted 2 perfect matchings. There are actually more perfect matchings in this graph. Can somebody count and tell me how many perfect matchings are there in this graph? Or just tell me how many you can find, and we will figure out if that is the correct number or not. So here is a hint. Observe that every perfect matching will have to use at least one of these 3 edges, 1, 2, and 3. Because there is an odd number of vertices on the left side and there is an odd number of vertices on the right side. So you have to choose at least one edge from this set. In fact, if you think slightly harder, you can observe that you have to use either one edge or you have to use all 3 edges. If you use all 3 edges, you get the green perfect matching. If you use exactly one edge, then the rest is actually determined automatically. If I use this edge, I have to use these 2 edges. So if I use this edge, but I don't use the other two edges, then I must use these two edges. And if I use, let's say I'll use a purple. If I use this bottom edge, then I must use these two edges. So that is your 4 perfect matchings. So you have to compute the sign of each of them and add them up. Okay? Fine. Of course, why is this a good idea? We will come to that point in a few minutes. Okay? But this is what is called the Pfaffian. I'll just put the term here. Let me use a different color. This is called the Pfaffian of an orientation. Okay. Any questions or concerns regarding the definition of the Pfaffian?
No.
Okay. So now I have a question for all of you. Supposing I can compute the Pfaffian of any orientation, when will it give me the actual number of perfect matchings? Supposing I can compute the Pfaffian of any orientation, what property should my orientation satisfy so that I get the total number of perfect matchings by just computing the Pfaffian?
All of them would have to be either 1 or -1.
Exactly. If all perfect matchings have the same sign, then I am very happy, because if I can compute the Pfaffian, then I have the number of perfect matchings. Right? And of course, I also have to find the orientation. But anyways, that is what I mean by a Pfaffian orientation. So a Pfaffian orientation, which is not the same as Pfaffian of an orientation. Sorry about that terminology. But by Pfaffian orientation, I mean an orientation where all the perfect matchings have exactly the same sign. And therefore, this orientation we chose is not a Pfaffian orientation. Okay, so let's go to a new page. What is a Pfaffian orientation? Of a graph. It is an orientation D of G such that all perfect matchings of G have the same sign. Sorry. With respect to the given orientation D. Okay. That is what is called a Pfaffian orientation. Any questions, concerns?
No.
Okay, thanks. All right. So why do we care about Pfaffian orientations? I mean, of course, it would be meaningless to talk about Pfaffian orientations if we cannot compute the Pfaffian of an orientation quickly, right? So let me just go back to the previous page. So we want to compute the Pfaffian orientation quickly, right? And then, of course, if we have a Pfaffian orientation, then we will get the number of perfect matchings easily. Okay, so turns out the Pfaffian of an orientation. So in fact, these things were not actually defined for graphs. They were actually defined for algebraic objects, and there are some results in algebra that basically explain the motivation for all of this. So I'm going to quickly tell you what is the connection between orientations and skew symmetric matrices. Okay, given any orientation, I will write down a skew symmetric matrix from that orientation. Okay, so let me erase a few things. I will erase the computation of sign. Actually, let me not do that. Let me just undo. Okay, I will just copy things and okay. 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 All right. So here is our orientation. And now let me tell you how this is equivalent to a skew symmetric matrix. My rows are going to be 1, 2, 3, 4, 5, 6. My columns are, of course, going to be 1, 2, 3, 4, 5, and 6. And let me first put zeros on the entire diagonal. Everybody knows skew symmetric matrices, right?
Can you recall once?
Yeah, so skew symmetric matrix, I'll just draw it and then tell you what the property is. But yeah, I will recall it in a second. First, I'll just put diagonals equal to 0. And now let me look at any edge over here. 1, 4. 1 is the tail and 4 is the head. So I will put a +1 in the row 1, column 4. And in the row 4, column 1, I will put a -1 because the tail is 1 and the head is 4. Okay, let's look at another arc, 5 to 2. So in row 5, column 2, I will put a +1. Row 5, column 2, I'll put a +1. And in row 2, column 5, I will put a -1. Okay, and if there is no edge between two vertices, let's say 3, 5, there is no edge. So in 3, 5 position, I will put a 0 and same for 5, 3, whatever. Observe that in this matrix, Aij is equal to minus Aji. This is the skew symmetric matrix. Questions, concerns?
No.
So do you all agree that orientations of a graph are equivalent to skew symmetric matrices where all the entries are 0, +1, -1? So it is actually not just all skew symmetric matrices. It is 0, +1, -1 skew symmetric matrices. I claim that any orientation of an undirected graph can be thought of as a skew symmetric matrix on the entry 0, +1, -1. And vice versa. Every skew symmetric matrix whose entries are coming from this set 0, +1, -1 can be thought of as an orientation of an undirected graph. If you are convinced, then we can move ahead.
Yes.
Okay, thank you. So just let's record this here. These objects are equivalent to oriented graphs. Okay, by oriented graph, I mean you take a simple undirected graph and you put a direction on every edge in order to get a directed graph. Okay, such graphs are called oriented graphs. Okay, so there is an equivalence between these two. And now here is what Cayley proved. I forget the year, but it must be many years ago because it's Cayley. So what did Cayley prove? Cayley proved that the Pfaffian of a matrix is simply the square of its determinant. The Pfaffian of a skew-symmetric matrix is equal to Pfaffian we have already defined for orientations. Same definition applies to skew-symmetric matrix. I will put a 0 plus 1 minus 1. Cayley's result actually applies to all skew-symmetric matrices, but I am just stating it for a special class of skew-symmetric matrices. Pfaffian of a 0 plus 1 minus 1 skew-symmetric matrix is equal to the determinant of the same matrix. Let's say the matrix is, I will call it D because it is equivalent to orientation. Then it is simply the determinant of that matrix squared. And why is this good news? Can somebody tell me why this is good news? Why should we be happy because of this theorem of Cayley?
Maybe because it's always positive, because it's this square, so we don't really have to deal with negative numbers.
That's one thing. However, remember that we are interested in Pfaffians because it counts the number of perfect matchings. If all the perfect matchings have the same sign. We don't know how to compute the Pfaffian, but what do you know about the determinant? What can you say about computing the determinant? Is that easy or is that difficult?
The diagonal is zeros. It's easy because all the diagonal elements are zeros, I think.
It's always easy, Gaussian elimination. Computing determinant is always easy because of Gaussian elimination. You can do this efficiently. Computing determinant.
So this is a doubt because the Pfaffian can be negative as well, right? So I had a doubt. Is it the
Yes, go ahead.
is it that the Pfaffian squared is the determinant?
Give me a second. I'll just check my 1 second.
I think it is, Nishad.
Yeah, I think determinant is the square of its Pfaffian. Yeah, I said it wrongly. My bad. Yeah. Determinant is the square of the Pfaffian. That is what I meant to say. Yeah, absolutely. The determinant is the square of the Pfaffian. My bad. Yeah, you're right. Pfaffian can be negative because you're computing the signs, you're adding up the signs of the perfect matchings. If you have more minus ones than plus ones, you will have a negative number there. Yeah, good. Yes. Good. Right, but the main point I'm interested in is that this is something we know how to compute efficiently. We know how to compute the determinant efficiently for any matrix, right? And therefore, if we had a Pfaffian orientation where the perfect matchings of all the signs are equal, then we can simply compute the determinant of the matrix, and then we can simply take the square root, and we will have the number of perfect matchings of the original graph. Does everybody agree? So the point I want to make is, whenever a graph has a Pfaffian orientation, this is a corollary of Cayley's result. If a graph has a Pfaffian orientation, of course, there is one small caveat which I have not addressed yet. I'll come to that. If a graph has a Pfaffian orientation, okay, I will abbreviate Pfaffian orientation to P dot O dot. Then its number of perfect matchings can be computed easily. There is one small caveat. Does anybody see that small caveat? I kind of cheated you on one small thing.
Are we talking about like the sign here? Because we do get like the number of perfect matchings, but then do we know like the sign?
No, so if I have a Pfaffian orientation, right, I will just add up the numbers. If I get a negative number, well, I just forget the sign, right? Because it is correct up to sign, right? So even if the graph has 5 perfect matchings, I may get 5 or -5. I just forget the sign, right? But there is another small technical caveat. My claim is not completely correct. There is some small thing I am lying to you about. Notice the hypothesis. If a graph has a Pfaffian orientation, but if I just tell you that this graph is a Pfaffian orientation, you still need to find the Pfaffian orientation. Do you agree? You still need to put directions and find the Pfaffian orientation, and then you can apply Cayley's result to get the number of perfect matchings. Right? Do you agree? Do you see the point here? Even if I know that the graph is a Pfaffian orientation, that is not enough information. I actually need to have the Pfaffian orientation in order to do the remaining part. Right? So we still need to compute the Pfaffian orientation. Knowing that it exists is not enough. I need to actually have the orientation in my hands in order to take the corresponding skew-symmetric matrix, compute its determinant, and then take its square root to get the actual number of perfect matchings, right? So we still need to find out what is this Pfaffian orientation. Turns out, if a graph has a Pfaffian orientation, then it is actually easy to find out. So if I promise to you that, hey, this graph I'm giving you definitely has a Pfaffian orientation, then actually there are techniques in graph theory that can be used to find the Pfaffian orientation, right? But it needs the guarantee that the graph has the Pfaffian orientation. Okay. Are there any questions or concerns? Is the main point clear here? Why do we care about Pfaffian orientations?
All okay.
Okay. So when you see a definition like this, of course, one natural question is, does every graph have a Pfaffian orientation? I have not shown you a single example of a graph that does not have a Pfaffian orientation, right? So of course, the answer is no. Every graph does not have a Pfaffian orientation. And I will show you an example with a proof. Okay. Manjil, how much time do I have?
30 minutes.
Okay, cool. The smallest graph that does not have a Pfaffian orientation. I will tell you what this graph is. But before that, what do people think about planar graphs? Let's go back to a few pages. Let us go back a few pages. Let's see what did we discuss. There are rich classes of graphs like the planar graphs for which number of perfect matchings can be computed efficiently. So what do people think? Do planar graphs have a Pfaffian orientation, or does anybody want to guess anything?
Wait for 1 minute. They're discussing.
Okay.
Okay, they are saying yes.
Okay. In fact, you're right. Kasteleyn in 1963, one of those theoretical physics people, proved that all planar graphs are Pfaffian. What I mean by a graph is Pfaffian is that they admit, every planar graph admits a Pfaffian orientation. You can orient the edges in such a way so that all perfect matchings will have exactly the same sign. They will all be positive or they will all be negative. Okay. So the smallest graph that does not have a Pfaffian orientation, it definitely cannot be planar. Does anybody want to guess what could be a smallest graph that does not have a Pfaffian orientation? I will give you a hint. I have already shown you that graph.
Is it the first non-planar graph that you?
Yeah, that's correct. It's K33.
So also, what do you mean by smallest number of vertices?
Yeah, you can minimize either number of vertices or number of edges and you will get the same graph. Yeah. The next one will have at least 8 vertices and the number of edges will definitely be more than K33. It will be more than 9 edges. Yeah. Okay. Any other questions, concerns? Okay, so I want to prove these two things to you. Let's see if they're going to be a bit tight in the next half an hour. I will try my best to at least give you a glimpse of both of these things. Everybody with me?
Yes.
Okay. So there is one issue, which is that sorry?
Can I interrupt? Yeah. So there was one
Yes. Yes.
concern which was that you did not show us a planar Pfaffian orientation for the previous graph.
Oh, I haven't. I will show you. Yeah, I will actually show that to you very soon.
Okay.
Yeah. So I will show that as part of the proof of planar graphs are Pfaffian. Okay. So the one problem is that the definition of Pfaffian orientations that we looked at, it is very, very non-graph theoretical. Let's just see. Good, let's go back to this definition. Observe that the definition requires me to look at every perfect matching, compute its sign, and then figure out whether all the signs are equal or there are two different signs, right? So this is kind of annoying. It would be nice to have a definition which is very graph theoretical, very visual. Of course, I'm biased being a graph theorist. I don't find this very visual. Okay. So my next goal is to get to an alternative definition of Pfaffian orientations. Okay. Okay, let me erase this. Towards an alternative definition of Pfaffian orientations. Okay. For this, I want to quickly check one thing. I want to check. Let me motivate this. Let me give you one example to motivate this. Supposing here is my graph, and I take two perfect matchings. Okay, I'm going to take two perfect matchings. Red and I'm going to take another perfect matching, blue. I want to ask you a question. What is the symmetric difference of these two perfect matchings? What do you see in the symmetric difference of these two perfect matchings?
Can you recall the symmetric difference?
Well, symmetric difference is all the red edges that are not blue and all the blue edges that are not red. Right? So in set theoretical terms, if these are my two sets, the symmetric difference is this. So what do you see in the symmetric difference of the red and blue edges? You see something like this. Do you agree? The symmetric difference of two perfect matchings, red and blue, is simply going to be a set of red and blue alternating cycles. They are going to be even cycles where the edges alternate between red and blue.
Right.
This
so
is not difficult to prove.
just 8.
Sorry?
Is it just 8?
8 edges which look like this.
Is it always there? Okay. No, you can go on.
Right? Does everybody agree this is the symmetric difference?
Yes.
The point is it is going to be a set of red-blue alternating cycles. This is actually an easy graph theoretical fact to prove. Okay, if you just think about it a bit, you are taking two perfect matchings, red and blue. What is the symmetric difference? You will soon arrive at the conclusion that it has to be just a bunch of even cycles whose edges alternate between being red and blue. Okay. So if I want to compare the signs of these two perfect matchings, M1 is one perfect matching, M2 is another perfect matching, and I want to compare their signs. How do you compare the signs? Just multiply them. Sine of M1 times sine of M2. This will be positive if and only if both signs are equal. In all other cases, it will be negative. Do you agree? If I want to just understand what is the product of the signs of the two perfect matchings, intuitively, it should be pretty clear. I should just pay attention to these edges. The edges that are not red, not blue, they don't contribute to the sign of a perfect matching. Do you agree? If you remember how we computed the sign, when we compute the sign of the red perfect matching, we just look at the red colored edges. When we compute the sign of the blue perfect matching, we just look at the blue colored edges. Right? So the edges that are not red and not blue, you can just throw them away. They don't matter. The edges that are in the intersection, they will actually not contribute to the difference between the signs. That is actually an easy exercise. Because this edge is both red and blue, I can just ignore it. I just need to look at this part. If I can understand what's going on in this part, I should be able to figure out intuitively whether the signs are equal or whether the signs are different. Okay. At this point, I'm giving intuition. I'm not giving rigorous proofs. Right. To make it into rigorous proofs, we'll need a lot more time. But is the intuition clear? So in order to get to this alternative definition, I am going to first look at even cycles. Let us look at even cycles. What are the Pfaffian orientations of even cycles? Even cycles are, in some sense, very simple planar graphs, right? Let's just take a look at an even cycle. Here is an even cycle. 1, 2, 3, 4, 5, 6. And there are two perfect matchings, the red perfect matching and the blue perfect matching. Okay. And now I'm going to consider an orientation of this graph. Let me make a copy. Okay. And let me put directions. I will use green color to put directions. Let's say I put all the edges going in the clockwise direction, where clockwise is this. What is the sign of the red perfect matching? M1 is my red perfect matching and M2 is my blue perfect matching. It is the sign of the following permutation: 1, 2, 3, 4, 5, 6. And let's see, 1 to 2, 3 to 4, 5 to 6. Number of inversions is clearly 0. And now let's look at sign of the blue perfect matching. 2 to 3, 4 to 5, 6 to 1. 2 to 3, 4 to 5, 6 to 1. And let's see what is happening. There are 5 inversions. One participates in an inversion with every other element. And so I get -1 to the power 5, which is -1. So is this a Pfaffian orientation or is this not a Pfaffian orientation?
It's not.
Not a Pfaffian orientation. So this one is not a Pfaffian orientation. Now let me ask you a quick question. Supposing I flip one edge, what will happen? Can somebody tell me, if I flip one blue colored edge, what will happen to the sign of the red and blue perfect matchings? What will happen to the red one? If I flip one blue colored edge, what will happen to the red perfect matching?
I think it will change to -1 because one of
The red one. Are you saying the red one will change or are you saying the blue one will change? I am flipping a blue colored edge. You're on the right track. I just want to know which one will change. Will both of them change or will one of them change?
As we are changing the blue one, I don't think the red one should change because it should not affect.
Exactly. Exactly. The red one will not change because I'm flipping a blue colored edge. However, the blue one will flip. If you just think about it, you will see that the blue one will become from -1 to +1 and the red one will remain the same. Okay, fine. So that will be a Pfaffian orientation. So let's go back to the original graph. In the original graph, if I just flip one edge, maybe this edge, then I have a Pfaffian orientation. Now, can anybody tell me what are all the Pfaffian orientations of even cycles? Now I'm asking you to make a leap of faith here. Can you think about what are all the Pfaffian orientations of even cycles? Think about this flipping observation. If I consider the set of all orientations, for every edge I can either direct it from U to V or V to U. Can you tell me what are all the Pfaffian orientations of an even cycle? I'll give you a hint. You should think about how many clockwise edges are there and how many anti-clockwise edges are there.
So one answer is n by 2 plus 1 for, or n by 2 for a 2n.
No, so I'm not looking at the number of them. I'm trying to ask what is the property of an orientation that will make it Pfaffian. Rather than the number, I want to know if I can just look at an orientation of an even cycle. And can I quickly decide, hey, this is a Pfaffian orientation and this is not a Pfaffian orientation. I don't want to look at the two signs, the two perfect matchings and compute their signs. I want to do something that is quicker. What do all Pfaffian orientations of an even cycle look like? I'm trying to get a more sort of graph theoretical answer here. And I want to think about clockwise edges versus anti-clockwise edges.
So, okay. So, several of them have said that the number of clockwise and anti-clockwise directions must be odd.
Exactly. That is exactly what I'm looking for. Yes. The observation here is the orientations of an even cycle, or rather, let me put it as a, yeah. An orientation of an even cycle is a Pfaffian orientation if and only if number of clockwise edges, I will call it clockwise arcs because we are talking about directed graph. Number of clockwise arcs is an odd number. And therefore, the number of anti-clockwise arcs is also an odd number. Okay? Everybody with me?
Yes.
So motivated by this, I am going to say that an even cycle is oddly oriented if it has an odd number of clockwise arcs and therefore an odd number of anti-clockwise arcs. Otherwise, I'm going to say it is evenly oriented. Okay? So such an even cycle, we will call it an oddly oriented even cycle. Oddly oriented even cycle. Okay? The only Pfaffian orientations are the ones where the cycle has been oddly oriented. Okay, for an even cycle. Now let's go back to our motivation. Why did we come to this point? Because we were trying to understand how do the signs of two perfect matchings compare. So now trust me, now this I've given you all the intuition. The details are actually very easy to figure out. The sign of M1 times the sign of M2, if both of these cycles are oddly oriented, they will have the same sign. If one of them is evenly oriented, their signs will be different. If both of them are evenly oriented, their signs will again become the same. So this is actually equal to -1 to the power of number of evenly oriented M1, M2 alternating cycles. In particular, if this number is 0, if there are 0 evenly oriented cycles, then I will get -1 to the power 0 plus 1, which means that the signs of the two are exactly the same. This is the part that you really need to remember. Okay? Can you still hear me?
Yes.
Okay. Yeah, I don't know. I just put the pen on my desk and something happened in Google in this Zoom meet, but I think it's okay. Yeah. Okay. Yeah. So this is the corollary of our observation. It is really not difficult to prove. It is just a matter of bookkeeping. There are no really new ideas except the ideas I've already given to you. The one main idea is symmetric difference of two perfect matchings is a set of red-blue alternating cycles. And the second important point to note is that for even cycles, the Pfaffian orientations are exactly the oddly oriented ones. If you take these two facts and you do a bunch of very routine bookkeeping, you will be able to prove this corollary that I've given you. Okay? And from here, we can actually get to a definition of Pfaffian orientations that is completely graph theoretical, where we will not look at any permutations or anything. Okay? I want to take you to that definition really quick. A cycle C of a graph G is, I will call it alternating. It is coming from the previous definition. It is an alternating cycle. It is an alternating cycle if, when I delete the vertices of this cycle, the remaining graph has a perfect matching. Okay, let me give you a quick example. Okay, in this graph, if you take this cycle, is this an alternating cycle or is it not an alternating cycle? What happens if you delete the vertices of this cycle from the graph? What will you get? You will get this graph. Is it an alternating cycle or is it not?
Okay, it's not.
Not alternating. Okay. On the other hand, take a look at this cycle. Again, a 6 cycle. No, this one is going to be, yeah, 6 cycle again. Good. What about this cycle? If you delete the vertices of this cycle, you get a graph with 4 vertices again, but now that graph is a perfect matching. Therefore, this is an alternating cycle. The point is, a cycle is alternating if and only if it can be written as the symmetric difference of 2 perfect matchings. Otherwise, it is not alternating. Okay, so that is where the term is coming from. Okay, and it turns out that Pfaffian orientations are nothing but the following. An orientation of a graph an orientation D of a graph G is a Pfaffian orientation if and only if something. Can somebody tell me, wild guess, make a leap of faith, tell me what I should write here? It is something about all alternating cycles of the graph. All alternating cycles of the graph need to satisfy a certain property. Remember, every alternating cycle is an even length cycle. What do you expect about the number of clockwise edges and the number of anti-clockwise edges?
They should be odd.
They should be odd. Every alternating cycle, if and only if, every alternating cycle of the graph G is oddly oriented with respect to the given orientation. This is a completely graph theoretical definition. You don't need to take any permutations. You don't need to compute number of inversions, nothing. You just need to look at all alternating cycles of the graph and check whether they have an odd number of clockwise edges and therefore an odd number of anti-clockwise edges. Okay. So this is a graph theoretical definition. Of course, the problem is the number of alternating cycles may be exponentially many, just like the number of perfect matchings. But well, that's fine. I never said that the definition or this equivalent formulation is directly going to solve the problem, right? But it gives you a purely graph theoretical way of looking at the problem. Are there any questions or concerns at this point?
No.
Okay. If not, I am going to quickly go back to what I told you.
Just to,
I don't know if I have, sorry.
just to remind you, you have 4 minutes.
Yeah. So I don't think I have time to do this part. But what I will do is, I will definitely do this part. Let me convince you that K33 is the smallest graph. That does, I mean, I won't convince you about the smallest. Okay, smallest is not difficult. If you assume this, then smallest is easy because K33 is the smallest non-planar graph that has a perfect matching. The other one is K5, but K5 has no perfect matching, so I don't care about K5. So I will convince you that K33 does not have a Pfaffian orientation. Okay? Everybody with me? So here is a drawing of K33. Let me draw this part differently. Here is a drawing of K33. Let me color the vertices so that you can see the colors. These are going to be 3 vertices of the same color. And the other 3 are of the same color. Does everybody see this is K33? Okay. I want to get a Pfaffian orientation of this graph. Of course, I want to get a contradiction. Okay. So let me do the following. Let me just focus on the green colored part. Okay, let me make a copy of this. Okay. I want you to observe that all these cycles, there are 3 cycles over here. Q1, Q2, and Q3. This 4 cycle, this 4 cycle, and the outer 4 cycle. I want you to observe that all of these 4 cycles are alternating cycles in the original graph. If you take Q1, for example, then the remaining graph is a perfect matching, which is this edge. If you take Q2, Q2 is the bottom 4 cycle, then the remaining graph after deleting the vertices of Q2 has a perfect matching. And if you take Q3, then the remaining graph will be these 2 vertices, and they are joined by an edge, and therefore they have a perfect matching. Okay? So all these 3 cycles are alternating cycles in the original graph. Q1, Q2, and Q3 are alternating cycles of K33. That means in a Pfaffian orientation, I will need to have an odd number of clockwise edges here, an odd number of clockwise edges here, and an odd number of clockwise edges in Q3, all 3 cycles. I would like to show you that this is not possible. Okay, let's see why. Sorry. So I claim that the number of clockwise arcs in Q3 is related to the number of clockwise arcs in Q1 and Q2. But what is the relation? I don't know. I'm going to ask you. Can somebody figure out what is the relation? I want you, the left hand side is given to you. I want you to figure out the right hand side. How can you use the number of clockwise arcs in Q1, the number of clockwise arcs in Q2, in order to compute the number of clockwise arcs in Q3? Let us label the vertices. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. You can see that if this is a clockwise arc in Q1, it is also clockwise in Q3. If it is anti-clockwise, one of these two arcs is anti-clockwise in Q1, it is also anti-clockwise in Q3. And it is, these arcs are not even counted in Q2. Q2 is only concerning with this 4 cycle, right? So we will be counting these outside arcs correctly. Whatever the directions are, we are going to count them correctly. The main problem is these arcs. This one, let me color them in some color. The main problem is these two fellows. They will be counted in Q1 and Q2 both, but they should not be counted in Q3. Can you try to focus on these two arcs and figure out the right hand side? Let's put one direction. Supposing this arc goes like this. Is it counted in clockwise arcs of Q1 or is it counted in clockwise arcs of Q2?
Q2.
It will be counted clockwise in Q2 and it will not be counted in Q1 because it is anti-clockwise for Q1. Now consider the other situation. Now look at this arc. I have directed it in the other way. Will it be counted clockwise in Q1 or in Q2? Right, you see it is counted clockwise in Q1. However, it is not counted in Q2 because it is anti-clockwise. So which means I am counting these arcs, no matter how I orient them, I am going to count them in exactly one of the two. So I need to subtract this 2. So I hope you all see that this is simply the sum of these two numbers minus 2. If these two numbers are odd, if these two are odd numbers, clearly odd plus odd minus 2 is an even number. So therefore, I cannot make all the 3 numbers odd. And that proves that K33 is not Pfaffian because you cannot make all the alternating cycles oddly oriented. And now if you go back to our theorem, every alternating cycle should be oddly oriented. So we can't do this for K33. So what we have proved is K33 is not Pfaffian. The fact that it is the smallest such graph, it is a corollary if you assume that all planar graphs are Pfaffian, but unfortunately, we don't have time to prove that. Of course, it is much easier. You can just check all the graphs on 4 vertices. You don't need to check graphs on odd number of vertices because they don't have perfect matching. So we don't care about those graphs. Yeah, so if I had more time, I would have shown you a proof of this, but I don't think I have time for it. If you're interested, everything I have covered is from this book that is recently published called Perfect Matchings by Lucchesi and Murthy. It is published in 2024. And pretty much everything I'm covering is from this book, chapter 19, if I'm not mistaken. Yeah, chapter 19. Okay, so that's all for today. Thank you. Are there any questions, concerns?
Hello, sir. Could you go
Yes.
to the slide where we define the alternating cycles?
Yes. Yeah, here.
So I did not understand why we defined it in such a way. Like what was
Right. Good point. So the reason we defined it like this is because we noticed that in order to compare the signs of two perfect matchings, I just need to look at the alternating cycles formed by those two perfect matchings. Okay, when I take the symmetric difference of those two perfect matchings. So if I understand all the red-blue alternating cycles, where red is a perfect matching and blue is a perfect matching, then from this corollary, I should be able to figure out when is it the case that all perfect matchings have the same sign. So the intuition is that we need to focus on cycles that are M1, M2 alternating cycles, where M1 and M2 are two perfect matchings. Turns out, if you want to understand these cycles, they are exactly the definition I gave you. So you can prove the following theorem. It's an easy fact to prove. A cycle, you can assume your graph G has a perfect matching. A cycle C is M1, M2 alternating. For two perfect matchings M1 and M2, if and only if the cycle C is alternating. That is as per the definition I gave in the other slide, in the other page. Alternating means G minus vertex set of C has a perfect matching. So we don't care about all even cycles. We only care about the alternating even cycles. And that is because of this fact here. Does that make sense?
Yes.
Okay. So yeah, there is a bunch of things I've skipped. One suggestion I have is if you believe this corollary, see if you can prove the alternative definition. Try proving yourself. Using the earlier corollary.
Okay.
Any other questions?
No questions for now.
Okay.
So thank you so much for the guest lecture. We can thank him by giving him another round of applause, please. Yeah.
Thank you very much. Yeah, so I think there was a lot of stuff in there, but the main issue is that just in order to translate from the algebraic world to the graph theoretical world, one needs to go through a lot of sort of basic things if you're used to graph theory, right? So it was a bit packed, but yeah, I tried to not overdo too much on the algebra or the graph theoretical side. So, but yeah, we did not cover a lot of things. If you're interested, there is a lot of stuff out there, and you can take a look at this book I mentioned. Yeah.
Okay. Thank you, Nishad.
Thank you very much. Thank you, Manjil. And thanks everyone for joining. Bye.